Alright, welcome back. Now let's go to tensile test. What we're seeing here, we're seeing the tensile test machine, then we are seeing the monitor here.
Phenomenon is to be tested. This is the test piece. It has a cylindrical test region.
This thing called the test piece or a sample. So the reason we're doing this tensile test is because you want to know the strength of a particular material. Like if you want to know the strength of mild steel material or aluminium or copper, you take the sample of that particular material and put it in that machine as we've seen before there. Then that machine is going to stretch it until this thing fails. So that kind of test, we'll call it destruction test. So what is the strength actually? The strength that I'm talking about, we're talking about the biggest force this particular material can handle. So if you want to know the biggest force this particular material can handle, you will have to take sample and put it inside
with an original diameter of 10 millimeters and an original gauge length of 100.
Put it inside this machine called the tensile test. So what is the tensile test going to do? Is going to grip this workpiece that you see here and then pull it until it fails. So what's going to happen is that as this machine, as you can see now, it's going to pull the component. The length of this is going to increase. So the length will grow from the size that you see right now to a bigger size. You will see that clearly at the end. So from this screen monitor that you see there, this one is going to give you what I can say, maybe a force versus change in length display or graph. So something like this, as you can see on the screen. So meaning that we are going to observe the change in length of this workpiece as you apply force. Then the force that you apply there is going to get increasing. So it won't be constant. So what we'll see here is that as the force increases, the change in length as well becomes more. So we're going to study that relationship of the force and the change in length. So the graph that you're going to see here is going to show you the relationship between the force that will be applied on this thing and the change in length. Right, as I don't want this to take long. Let's go straight to our area of interest. Okay, this is the graph. That gives the relationship between the force applied and the change in length. So you will stop doing this test immediately after this thing gets broken, as you can see there. Right now at the moment this thing is broken. So this thing is broken. So now what we are seeing here, it's an identical test piece. So this piece, this one, before it becomes like this, it was like this. So we took this thing like this and inserted it into that machine pulled it until it gets broken. So now we're going to discover two things. By comparing this one and this one, we're going to discover two things. So the first one is the length. So as you can see, before this thing was shorter, as you can see the length of this, it's shorter. We're going to have this thing called the gauge length. So like if we say this is the gauge length from here to the straight line, it means that we're going to focus on this length. This is our area of interest. So when we do this test, our area of interest will be from this, from that to there. So which is this part here and then this part. So when you compare, this is the original length. When we're talking about the original length, we'll be talking about this. And then after pulling this thing, finally the length will have this size. So this is the final length. So this LO, we call it the gauge length. So which indicates the length that we are interested with. So we want to study that particular length, right? From this, now we can see that the length has increased, and then this part that you see here from here to there is going to be the change in length. So the change in length will be the difference of the two, the final length minus the original length. So while we're still on this length thing, the common question in this chapter section, it will be to calculate the percentage elongation. So percentage elongation. Which is going to be the final length minus original length over original length multiplied by 100. So we call it percentage elongation. So in other words, we want to know that after the fracture or breaking, the length, this original length has increased by how much in terms of the percentage. Like if you have this length, original length, this size, if we take this and pull it, and then the length increases from here to this size. So if you want to know the percentage elongation from the look of things with your naked eye, you can see that this new length is almost double size of this original length. Therefore, in this case, the percentage elongation is going to be 100% because the length has doubled. So if you had original length of this, then you take that and pull it, the length increases from that size maybe to this size. So from the look of things, let's say this one is 1 meter. If from here to there is 1 meter, then from here to there is 1.5. That means this thing has increased by half. So this length from here to there, which is the change in length, equals to half of this original length. So this is original length. So we can say that this length equals to half of that original length. So if this thing has increased by half of the original length, then the percentage elongation is going to be 150. So how are you going to get that 150? Remember, from here to there is 1 meter. Then we're going to say, if you follow this, we're going to say the final length, which is 1.5, minus original length, which is 1, over original length, which is 1, and then you'll get 0.5 over 1 multiplied by 100, which is 50%. So in this case, it means that the length will increase by 50% or by half. Right. Again, what you can see now, if you check this portion here, this portion, which is roughly going to be this part here. When you check here, originally this thing, it had the bigger diameter. So this diameter that you see here, we're going to call it the original diameter. This is the diameter before pulling, before we apply that force. Then after applying the force, we're going to have what we call the necking. So this thing that you see here, it's a neck. This is the neck. So this part, this diameter from here to there, we're going to call it the final diameter, which is the diameter after breaking. So after the breaking, this diameter here will be reduced from this size to this size. So as you pull this thing, the neck will develop here. The diameter will start to become smaller until it breaks. So this is what we're going to call the final diameter. So now they will ask you to find the area reduction percentage. In other words, they will try to find or how much did this area get reduced in terms of percentage. The area was reduced by 50%, by half, or what? So that's what we'll be trying to get here. So to find that area reduction, we're going to use this formula. We're going to say original area minus final area over original area. Right, so don't be surprised here. Look here, we started with original minus final, but here we started with final minus original. So the reason we do this is because we start with the big one minus the small one. We avoid the negative. We are trying to avoid negative. So to avoid that negative, always you start with the big one. So in this case, the big one here will be this. Then the small one, it will be this. This time I say it's small. Here is big. So we start with the big one. The big one will be the original. Right, it's just that in most cases, we're not going to use this formula. You can use it, but it's going to be longer. So instead of using original area minus this over that, we're going to say that original area, we're going to replace it by pi original diameter squared minus area is pi d squared over 4 divided by 4 minus pi. Now I'm coming to this final area here. Final area will be diameter, but we're going to use this diameter here, which is the final diameter after breakage, squared over original area, which is pi d squared original diameter squared over 4. So from this you take out pi over 4 as common factor here. You take out pi over 4 as common factor. Then that pi over 4 will divide with this. and then you will remain with original diameter squared minus final diameter squared over original diameter squared. Right, that's how we are going to calculate area reduction percentage. So this is the formula that we are going to use in most cases to calculate the area percentage reduction. Right, let's go to these two questions here. Right, let's check this question. This is number 8. So they give you a load and then extension. So meaning that by applying the force of 2.3 on that workpiece, this length will change by 0.0056. Then as you increase the length to, the force to 9.3, the change in length as well will be this much. So as you increase the force to this much, the corresponding change in length will be this much, and so forth. So this is what normally we're going to get from the monitor, from the tensile test. So the tensile test normally it's going to give you the graph of load versus extension. So now the gauge length is the original length, and then this gauge length is the original length. I spoke about it. This one is the original diameter. I spoke about it as well. So you've seen it, I've shown you on those pictures. Number A, now draw the stress strain graph. Draw stress strain graph. Right, so since the question said we must draw stress strain graph, then we have to change those given forces to the stresses. Remember, they gave us these forces. They gave us this extension. So now they said we must draw stress strain graph. Therefore, we have to change these forces to stress. So we're going to use this formula. Stress, we know that is force divided by area. So the area that you see here, it must always be the original area for your syllabus. Right? So the original diameter is given, it's 13. They give us original diameter as 13, then we'll take that, you replace it with it here, you get the original area. Therefore, now to convert these forces to stress, use this formula. You just have to take all these forces, all of them, 2.3, 9.3 individually, you take them and divide it by the area. Take 2.3 divided by area, you get 17, and so forth. You take the next force, 9.3, divided by the area, you will get this stress. Then you take this force divided by this area, you will get this. You take this divided by this area, you will get this. You take this, divide by this area, you will get this. So this is the stress. Now here, this is the strain. So strain, this is the symbol for strain, will be equals to the change in length over original length. So original length is the gauge length. So what you will do here, you will take this change in length. This is the extension or the change in length. You take this, you divide it by the original length. So take 0.0056 divided by original length. So I don't remember the original length there. So the original length, its gauge length, which is 60. Oh, where am I? It's on that thing. Okay, it's fine. Strain. Strain will be the change in length over original length. So the change in length, these are the change in length, but you'll take this first one, 0.0056 divided by original length, which is 60. Then you will get this. Then from there you take this, divide by 60, you'll get this. You take this, divide by 60, you'll get this. You take this, divide by 60, you'll get this, and so forth. So now this is the strain. This is the strain. So now we're going to use this. We're going to use this stress. This is strain to calculate, to draw the stress strain graph. So stress strain graph, we're going to draw a line like this, vertical line, horizontal line. This side will represent the stress. This side will represent the strain. So we'll just plot this thing like this. You'll just have to draw this thing maybe according to scale. You can say here maybe it's 20, 40, 60, 70, or we can use, for the good value will be 50, 50, 100, 150, blah blah blah, and then this side you plot the extensions. This side represents the extension. Okay, now we're going to have the challenge here. So when you check these things here, this one is to the power negative 5. This one is to the power negative 4. To the power negative 4. To the power negative 3. To the power negative 3. So before you plot the graph, make sure that this exponent here is the same. This one is negative 5 and negative 4. So if you use negative 4, make sure that these values are multiplied by exponent, are multiplied by 10 to the power minus 4, all of them, 10 to the power minus 4, 10 to the power minus 4. So yeah, so now let's say you use this one at 10 to the power minus 4. Let's try to use this one of 10 to the power minus 4. Okay, so if you want to convert this thing to 10 to the power minus 4, you are going to take this comma here and shift it to this side. You move this comma from here to here. So if you remove this comma from here, you erase it, you move it to there, then we're going to have 0.9. And if you move the comma from here to this side, when it comes to this, you add 1, you'll say plus 1. Then you're going to have 0.9 multiplied by 10 to the power. You're going to have negative 5 plus 1 is negative 4. So if you want to convert this thing to 10 to the power negative 4, I'm on this one now. You take this comma, shift it to here, you move it to here. You erase this one, you are going to have 11. Now. You are no longer going to have 1.1, you're going to have 11. So if you move from here to this direction, you subtract 1 here. Then you are going to have 11, 11 times 10 to the power negative 4. Negative 3 minus 1 is negative 4. Okay, let me repeat this. Here initially we had this. Then I said that if you take this comma, you move it from here to there. Check the direction. We take it from here to there. You'll have 0.9. Then here you add 1. So negative 5 plus 1 will be negative 4. But when it comes here, it's different now. When it comes here, we're going to move this comma from here to there. You put it here. So you move that comma in that direction. So if you move that comma in that direction, we are not going to add, we are going to subtract. You say minus 1. So we're going to have 11 times 10 to the power 10 minus 4. Minus 4 is negative 3 minus 1. So that's how you convert these things. So the same thing here, you will have this thing will be equals to 14,98 times 10 to the power minus 4. So here you can write times 10 to the power minus 4. Okay, anyway, the graph is drawn already for you here. Here's the graph. What's happening now? I think these values here, they were supposed to be 50s, not what we're seeing here. Yeah, it was supposed to be 50, 100, 150. Remove this. Right. Yeah, the first thing that we had there, don't remember very well, but it was 0.9. Somewhere here it's 1, 0.9 and 1 almost at the same point. You'll have 0.9 on this side. On this side, I don't remember very well, but I think it's 17. So you mark 17 from this, or draw a line like this and like that. This will be the first point. Then the next one, let me just go there again. So we plotted this 17 and 9.3, 0.9. The second one, it will be 70 and 4. So you will come to the graph. 70. Let me write them so that I won't forget when I go down there. 70 and 4, 139 goes with 7.6. 207 goes with 11. 278 goes with 14.9. Right, so this is the graph. The next point, it's 70. If this is 50, 70 will be somewhere there. So it will be 70 and 4.1. And where they meet is point number 2. The next point will be 139 and 7.6. So this is 150, 139 will be there. Then you check 7.6. Somewhere here, this is 6, this is 8. Somewhere here will be 7. 7.6 will be somewhere there. So where they meet, it will be a point. The next one will be 207. 207. This is 11.1. So 11 will be somewhere in between, 11.1, somewhere there. Where they meet is a point. The next one, 278. This is 300 there, 278. This is 14 point something. So this is 14 point something. So after having this, you join this thing using straight line. So that line will go via these dots like this. Then this will be the stress strain graph. Stress strain graph. Then you will get to a full marks for like by doing that. So make sure that you indicate that on this side is stress values, like that. On this side it's strain. Right, the next question will be to calculate Young modulus of elasticity. So which is the gradient, or which is the slope? So you can do this thing the same way you used to do maths N1, or like saying this. Remember, gradient is the change in y over the change in x. So you can say this, if you consider these 2 points here, remember this one maybe it was this 50, 100, 150. So this one is 139. You can say 139 minus this one was 70. 139 minus 70 equals to, this was 7.6 minus 4.1. So you can use this 139 minus 70 over 7.6 minus 4. Yeah, but anyway, we don't prefer to do it this way. What we normally do, we just choose any point along this straight line. So normally this stress strain graph, it will start by a straight line, as you can see. Then as it goes up, it will become a curve like this. So normally this graph will go like this. It will start like a straight line like this, and then after some time it changes to a curve. So it's just that for your syllabus, always this graph will be straight line. Your syllabus only covers from here to there. So to calculate E, which we're going to use what you call the Hooke's law. Hooke's law, which will be given by the stress over the strain. So this formula is only valid where you'll have the straight line. So whatever point that you're going to use to calculate E, that you're going to choose, it must be within this straight line. Don't choose a point here or here or here. You choose any point from between this point and this one. So like if you choose this point here, this one, we're going to check, draw a horizontal line like this and check this is corresponding to what value of stress. So this is 50, 150, this is 150, this is 200. So it's between 150 and 200. Maybe you'll have 175. So you'll say 175 divided by, this is strain. Strain is on this part. So you draw a horizontal line like this. You check this thing is corresponding with what. So this is 10, this is 8. Hopefully this is 9. So it will correspond with 9. So this 175 divided by 9 will give you the value of E, modulus of elasticity. So you just choose any point. Like here they chose a point of 75. So remember this is 70. So 75 will be somewhere there. So oh no, they have to choose this point first. Then you draw horizontal line, you check it correspond with 75. You draw vertical line, it will correspond with 4. So 75 divided by 4 will give you E. So that's how you calculate the modulus of elasticity. So the next question, calculate the percentage reduction in area if the diameter of the rod was 8.3 at fracture. So I've already discussed the formula to calculate this. Let me do it here. It will be the original squared minus the final over the original squared multiplied by 100. So that's how you calculate this area percentage. I spoke about it. So you just have to substitute. Original diameter is going to be 13. Then you're going to have 13 squared minus the diameter at fracture. This is the final diameter. 8.3 squared over original diameter 18 squared. Then whatever answer that you get, you multiply it by 100 to get percentage. Right, you'll do it. You are done with this number C. We are done with number C. We can quickly just check number 9, even though that is more or less the same as the previous one. Right, with this one, the following results were obtained by means of tensile test on a carbon blah 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 blah. Original diameter 30, original length 50, at the limit of proportionality. The load at the limit of proportionality will be this 90. Extension at the limit of proportionality will be this. The load at the yield point was 104 kN. Number A, calculate the stress at the limit of proportionality. So at the limit of proportionality is where this straight line ends. So as I've said, the graph will start like this as a straight line. And then after some time, it will start to have a curve like this. So where straight line ends, at the end of the straight line, this point, we are going to call it the limit of proportionality. So if you draw horizontal line, the stress that will be here will be, the force. This side will be 90. And then this side, the extension will be 0.0443 at the limit of proportionality. So now calculate the stress at the limit of proportionality. At the limit of the stress will be equals to force divided by area. So at the limit of proportionality, the force will be 90. Area, you take the original diameter, which is 30. You calculate area using that diameter. Then the stress at the limit of proportionality will be 90 divided by that area. Number B, calculate the Young modulus for this specimen. The Young modulus, I said that to calculate E, you can choose any point as long as that point is within this straight line. So you can just choose this point or this one. Don't choose this one since the straight line ends here. So don't choose any point beyond the straight line. So now you can choose this thing is fine, but the problem now is that if you choose this point here, we don't know the value of the force that is corresponding to this. Then we don't even know the value that will be the change in length that will be corresponding to this point. So now, because we know this point, at this point, at the limit of proportionality, we know the force and the change in length, then we have to take the advantage of this. Remember, this point is still on the straight line, but it's just at the end of the straight line. So as long as it's still on the straight line, we can use this point to calculate E. Then we're going to use that point, and then at that point, we know the force. But we're going to use this force to calculate the stress, which is this. Remember, E is stress over strain. It's not force. It's not force 90 over change in length. It's stress over strain. You must get stress first, which is this part here. Then you must get the strain. Strain, remember, will be equal to the change in length, which is this, divided by original length, which is 50. You will get the strain. After that, you take that stress divided by the strain, then you will get E. You will get E. So number C, the maximum tensile stress in the specimen if the maximum load recorded was 180. So they gave you maximum load or maximum force. Then we're looking for maximum stress. So you will still use the very same formula. Stress, it's force over area. So only difference now is that if you're looking for maximum stress, you must use maximum force or maximum load. So they give you maximum load. It's 108. You take that 180 divided by the original area. You will get the maximum stress. So that maximum stress, normally on the graph, it will be here. So this point will represent the maximum stress or maximum load. So which is going to be the strength of this material. So this means that this is the biggest force. This is the biggest, shows the biggest force this material can handle before it breaks. So when we say give us the strength of this particular material, we have to read the value that will be corresponding to this point. Right now, the percentage elongation of the specimen if the length of the specimen just before fracture is 68. I've discussed this formula as well before. So percentage elongation, we're going to say the big length, which is going to be the final length. I've shown you the picture over original length divided by original length multiplied by 100. So the original length, the final length, it's given at 68. 68 minus original length, it's 50 over original length, which is 50, multiplied by 100. Then you'll get that particular percentage. So that's all about this section. Yeah, thank you.